for the person that makes the rest of the class average go down, the outlier?
Yeah, the curve buster.
Gotcha. I'm gonna be
All right, I'm missing this. Let me just give up this one. All right, so let me get situated, and then we'll go live camera action. All right, so welcome. Today is Thursday, April 1st, and I'm not fooling you on that. It really is April 1st today. It's April Fool's Day. I'm not fooling
I
you.
forget that April
All right.
Fool's was a thing.
Just kind of stay with me here today. I know it's a Thursday and it's tired, but. Okay, so today we need to talk about phase changes. Okay, we've been talking about just the different states of matter, solids, liquid, gases, what causes them. We looked at some characteristics of liquids, of capillary action and surface tension in class on Tuesday. But today we want to talk about phase changes. How do we go from a solid to a liquid to a gas? And so when we look at, if I just look at, say this closed bottle of cleaner right here, okay? I'm trying to get out of the light. Is there anything up above the liquid in here? Air. Anything else?
Probably some evaporated, whatever.
Probably some evaporated water, because this is probably water with some other stuff in it. So the water is probably evaporating out of here. So there's a certain amount of water vapor. Now what is a vapor? I think I defined that for you earlier in the year. It's like a gas, but it's not. Think of what do you hear referred to as a vapor? Obviously water vapor, gas vapor. Anything else?
Something that's a gas that's not normally a gas at room temperature.
There you go, very good. Something that is a gas that's not normally a gas at room temperature. It's normally a solid or a liquid. So water is normally a liquid, but when it turns into a gas, we call it water vapor. Gasoline is a liquid at room temperature. When it evaporates, it's gasoline vapor. Alcohol vapor. Because when you put alcohol on you and it evaporates, you have alcohol vapor. Vicks Vapor Rub. Stuff you put on your chest, it's a solid, but then it vaporizes, the menthol eucalyptus. Okay, you can smell it and it clears your sinuses. Okay, so a vapor is just the liquid that's now in the gaseous state. So anytime you have a liquid, it's going to be evaporating at a certain rate, and you're going to get a certain amount of vapor above the liquid. So we're going to have a vapor pressure. Now what again causes pressure? What is pressure?
Collisions.
Collisions with the container walls, right? And if we have more vapor up here, what does that mean about collisions? More collisions, so what does that mean about pressure? More pressure. So the more the vapor evaporates, the more concentrated it is above the liquid, the higher the vapor pressure is going to be. So what do you think determines the rate, how fast something evaporates? Why does alcohol evaporate faster than water? What bonds? When water evaporates, when this water, I'm working on getting this water to boil, when this water boils, what's in the bubble? See these little bubbles? So this steam's coming off, right? Is steam hydrogen and oxygen gas? What is steam? Water still, right? So we're not breaking the covalent bond between the hydrogen and the oxygen. We're not decomposing the molecule, if I can. We're not breaking it apart from the hydrogen and the oxygen. When water boils, what are we doing? Breaking the water from the water from the water from the water. And those are what types of bonds holding them together? IMFs. And for water, we have all three: hydrogen bonds, dipole-dipole, and London forces. So the strength of the bond between the liquid molecules, and those liquids are generally always covalent substances, so we're always talking about IMFs. The strength of those IMFs determine how fast it evaporates. the faster something evaporates, the more vapor there is above the liquid, so the higher the vapor pressure. So, the pressure exerted by a vapor above its liquid is called its, what?
Vapor pressure.
Vapor pressure.
We didn't do 12 of them.
I thought we did.
We finished off on 12 and we were like, oh dang, that's the good stuff. Right
No, we
before
didn't.
we-
We finished 11.
We left, we were about to do 12.
Okay, I'll come back to that then. Because I got to talk about bowling, so I'll talk about how we measure these things there. And I forgot to get an important piece of equipment again. Okay.
See you beautiful.
Well, it's because I gave it away to another teacher to use, and I said, oh, I'll just go get another one. And
You got a trumpet, you could signal him.
How could it make it
Okay.
good for them?
liquids that have a high vapor pressure have what type of attractive forces? Low, because there's a lot of vapor. That means it's evaporating quickly. Okay? So the higher the vapor pressure, the weaker they have weak attractive forces holding the molecules together, while liquids with low vapor pressures have strong, weak or strong, low or high. Increasing the temperature. Remember our Maxwell-Boltzmann temperature distribution graph. Okay? Again, theoretically, if I had drawn this to scale, the area, the total space underneath this blue is going to be exactly the same as the space underneath the red. This is that area represents the number of molecules. And this is their kinetic energy, which really means their speed. Now again, because there's more molecules up here at the higher speed, at the higher temperature, that means that there can't be the whole area has to come down some, because the two have to stay equal. You always have the same number of molecules in a closed container. So it always shifts to the right. This is T2. This is T1. T2 is greater than T1. Okay? So as I increase the temperature, let's just say this is the energy needed to evaporate. Okay? Well, we have a whole lot more molecules that have enough energy to escape, to break the IMFs at the higher temperature, so it evaporates quicker. So we have, at higher temperatures, we have more molecules above the liquid. So as a result, it has a higher vapor pressure. Okay? So, increasing the temperature of a liquid increases the kinetic energy of the molecules. That's what this graph is representing. Okay? Giving them enough energy to break the bonds holding them together. This causes the vapor pressure to increase. So we increase the vapor pressure by increasing the temperature. All right, we're going to look at a couple other graphs. Before we do that though, if I have a beaker, I have my water molecules all around in here. These are all water molecules. Okay? And they're constantly moving and bumping into one another. Okay? Some speed up, some slow down. Kind of like a pool ball. You know, the cue ball hits the other ball, the cue ball slows down, the other ball speeds up. Okay? But the total energy in the collisions are perfectly elastic, so we don't lose any energy due to friction. So they're constantly speeding up, slowing down, but we have an average kinetic energy, an average temperature. Okay? Most of the time here, they don't have enough to break completely apart, but the ones sitting right along the surface, just kind of chilling out, floating on the surface, every once in a while, they can get hit by a high-speed molecule from underneath. That all of a sudden gives it enough energy to overcome the attractive forces, and it goes flying off. So evaporation is the escape of high-speed molecules from the surface of a liquid. And I don't think that's on there anywhere, but we need to write that down. And this is gonna be a key, from the surface of a liquid. So you wanna go play basketball in your driveway, but it just rained. And you got a big puddle. How do you make that puddle evaporate faster?
You get like moved around.
You move it around, right? You kick it with your foot and spread it out. Because evaporation can only occur from the surface. So if it's deep, you only have the molecules on the surface, but if you spread it out and make more surface area, then the molecules can evaporate more quickly because more of them are going to be on the surface. Same thing on the tennis court, you squeegee it, you try and push the water off to the side. Okay? So it's the escape of high-speed molecules. So as the high-speed molecules leave the surface, what happens to my average kinetic energy? Does it go up, down, or remain the same? If I take a class average of a test grade, I get a class average. Then I take all the high test grades out. What's going to happen to my class average? It's going to go down, right? So if I take the high-speed molecules out, if I take some of these out, the average is going to decrease. So what's going to happen to the temperature of the liquid? It goes down. Evaporation is a cooling process. Give me a common example of that. When you sweat. The reason you sweat is so the water can evaporate. As that water evaporates, the high-speed molecules leave, cooling you off. It takes energy to break the hydrogen bonds, and that energy comes from your skin, so you cool off. It's an endothermic process. Wow, some of y'all are saying, wow. Blowing your mind now. Something else for you to have to ponder while you're out, running, sweating.
We need a life lesson for that.
No, but I will say that, endothermic processes are cooling. I wanted to start a new little, like Snoop Dogg or frizz on my nizzle or whatever he used to say, when you say that, man, that's really cool, I want to say, man, that's so endo, or man, she's really hot, ooh, she's so exo, so, but it just hasn't caught on very much. So, I'm also going to do, you've heard of Weird Al, right?
Yeah.
Okay, he does all the spoofs like of Michael Jackson songs, and like Beat It, he does Eat It, and the different ones. I just actually heard this song on the radio. Don't you wish your girlfriend was a freak like me, or something like that? And so I want to do a Weird Al of that. Don't you wish your boyfriend was a geek like me? Don't you wish your boyfriend loved chemistry? Don't ya? Don't ya? I'm sure I could go through the whole song and come up with, good geeky lyrics. You just got to learn to revel in your geekdom. And so at some point you'll, because the other people are going to be working for you. So, that's like Vanderbilt's football cheer. That's all right. That's okay. You're going to work for me one day. When they're losing. So anyway, all right, I digress. So, I can't even remember where I was going with this. So evaporation is a cooling process. That's where I was going. That's why we sweat, is because as it evaporates off our bodies, okay, it cools us off. Now, let's look at a graph in your book. Just about vapor pressures. Well, if I can find it. There it is. We got too much jump. So here's a graph of vapor pressures, diethyl ether, okay? And just so you know, diethyl ether is going to look like this, C2H5, C2H5. And then ethanol is going to look like so they're just hydrocarbons. Notice that this has no real OHs, no hydrogen bonds in this one. This one has one place for hydrogen bonds, and obviously we know water looks like this, and it's two places for hydrogen bonds, and it's highly electronegative, so we have very strong dipole-dipole attractions and strong hydrogen bonds here. So, which one has the strongest attractive forces? Water. So at 40 degrees, well, let's just even say at 20 degrees, if we go up, notice that water's vapor pressure is here, alcohol's vapor pressure is here, but diethyl ether's is way up there. The weaker the attractive force between the molecules, the higher the vapor pressure at any given temperature. We with? And then as you increase the temperature, you always increase the rate of evaporation, so you're always going to be increasing the vapor pressure. So, evaporation only occurs at the surface. But now this water is boiling. Where are the bubbles forming? On the bottom. So what did we decide was in the bubble? Water. That's turned into steam, so it's water vapor. Okay? Now what's happening? What temperature is it right here?
Like 250 over, like 250.
Come on, what's the boiling point of water? 212 Fahrenheit. What is it Celsius? 100 degrees. Okay? So what do we expect this temperature to be right here? Close to 212? Is it almost boiling?
212 or above.
212 or above, which is 100 degrees Celsius. Okay? So Clay, come up here. You're gonna be on camera, so let's mask up.
Yeah.
Even though I just announced it.
My fault.
Okay?
Yeah, it's above 100.
Well, yeah, but the question is it going up anymore?
No, it's like right there.
It's like right there.
Yeah, like
Okay.
102-ish. It's just sitting there.
But it's not, but I'm still heating it up,
Yeah, but it's staying the same.
but it's staying the same. Wow. Okay, thank you. Did great. Why is it staying the same?
Evaporating is.
It's cooling itself off, but it's heating up so it cancels out.
So what's the energy going in to do? Being used to do? To evaporate, what has to happen in terms on a molecular level?
The molecules on the surface.
Constant.
Do what?
It's a constant heat.
Well, we're adding heat to it, but the temperature's remaining constant. We generally think of as we increase the temperature, we increase the heat, we increase the temperature, but this isn't happening here because it's still right at, it's supposed to be at 100, but the thermometer's not very accurate. And so we're breaking bonds. Remember, we have a difference between kinetic energy and potential energy. Flashback to first 9 weeks. Potential energy and kinetic energy. When you have a temperature change, you're changing kinetic energy. But when you break bonds and form bonds, when you have phase changes, when you're breaking bonds, forming bonds, it's always a change in potential energy, which is what we call latent heat. It's hidden to the thermometer. That's what the word latent means. I don't know if you've ever heard someone say he's got latent potential. That's potential that's yet to be seen. That person hasn't, lived up to the potential that's inside of them. Okay, you got a lot more there that just isn't showing yet. So that's what the word latent. So latent heat, it's hidden to the thermometer. There's energy going in, but it's used to break bonds. So just like this rubber band, and I used this example before, just like this rubber band, I do where I put energy into it, okay? It now has, I've changed its position, it now has potential energy to come back and release that same amount of energy I just put in, okay? So I'm putting energy in to break the water molecules apart. They've gained that as potential energy because now they can condense and come back together and release that same amount of energy that we're putting in. Have you ever wondered, like we have a freeze warning tonight. Some of the orange, or pardon me, peach trees in Clanton may have already begun to bloom. And now the freeze could potentially, destroy the crop. So what do? They put back, but they spray with water. I said, that's the most asinine thing I've ever heard. Why would they spray with water? It's just going to make the freeze, make it even worse. But what they know is that when that water freezes and the water molecules come back together again and form the bonds, that's going to release the energy that you had to put in to melt it. That energy gets released to the surroundings, and the surroundings, the little peach. And so if it's just a mild freeze like it's supposed to be tonight, that water freezing actually releases enough heat into the peach to keep it from freezing. And it provides an insulation from the rest of the cold air. Now, if it gets down to 20 degrees or 15 degrees, that system won't work. But at 30, 31 degrees, it will. Okay? So it's just that energy going in. Now, let's talk about boiling. Another great diagram. When water molecules here, if the water molecules push apart from each other and they form a bubble, they spread out, right? That's what gases do. When a liquid becomes a gas, the molecules spread way apart from each other. What's going to happen to the level of this liquid right here? It wants to rise up, right? But the atmosphere is pushing down on the surface of that liquid, saying, no, sorry, you're not coming up. So that bubble can't form. So the molecules, as you heat them up, they can escape from the surface. You started seeing, when I began heating this up, you began seeing the steam coming off before the bubbles form, because this high-speed ones can escape because they don't have to make the liquid go high, so the atmosphere can't stop them, but the bubble can't form. But as I continue to heat the water, they're playing, Mr. Graver was just playing Rocky, and that's what I always kind of say, you got that Rocky theme going on, okay? And by the way, have y'all all seen Rocky 1, the original Rocky? Okay. The most motivational for any athlete, for any person, the most motivational scene in that whole movie, probably in all movies of all time, is when Rocky gets up at 4 a.m. in the morning, does his raw eggs in the glass, puts on his sweaty, smelly sweatshirt, goes out and running in the street with no kids, it's in the dark, no fanfare, and he gets to the top of those stairs, and he's got a cramp, and he's hurting, but he doesn't quit, and he turns around, and he runs back. And he just keeps doing that. Nobody watching, nobody cheering him on, just self-determination to get better. That right there is what makes a champion. Is what are you willing to do when there's no one cheering you on, there's no one there watching? Are you willing to put in the work? If you are, you're going to be a success. Anyway, there's my life lesson for today. So, as I continue to heat this up, the water molecules, listen to Rocky, feeling strong now, getting stronger and stronger. As the water molecules are moving faster and faster, they're pushing out with more and more force. The atmosphere is starting to struggle to hold the liquid down, until finally the vapor pressure of the water equals the atmospheric pressure, and so it pushes out with the same force the atmosphere is pushing down, so now the bubble can form. So boiling is defined boiling occurs, what did I just say? With two spaces, when the blank blank is equal to vapor pressure of the liquid is equal to atmospheric pressure. Okay? So, normally we make a liquid boil by increasing the temperature until it's vapor pressure. Now, when I come back and I look at this graph that we were just at, which how long it's going to take me to find it again. So when I come to this graph again, vapor pressure equals atmospheric pressure. Notice the diethyl ether is going to, the vapor pressure, since it's higher at any given temperature, is going to equal atmospheric pressure way before water does. At like 20 something degrees here versus 100 degrees. So the higher the vapor pressure, the lower the boiling point. So there's three things that you need to know the relationship between. The weaker the attractive force, the higher the vapor pressure, the lower the boiling point. The weaker the attractive force, the higher the vapor pressure, and the lower the boiling point. Now, normally I said we make something boil by increasing the temperature. But what if I just lower atmospheric pressure? It's going to boil at a lower temperature. So this is a vacuum pump. Okay? I can honestly say that this thing just really sucks. Okay? I'm on fire today. What can I say? All right. So, if I can find the on-off switch. There we go. So I'm going to open up the valve. Now I'm sucking all of the air out of here. So now there's nothing pushing down on the surface of the liquid. I'm sucking the air out of it. Okay? So basically, I'm lowering this line. Now look, if you need to get out of your seat, come look. Zoom in if you need to on that. The water's boiling, isn't it? Did I heat it up at all? Is the water hot now? No. So I turn this off. Let the air back in. And by the way, while there's a vacuum, I mean, the air is pushing down on the surface of this thing 14.7 pounds per square inch. So it's not suction on the inside holding this down. It's the pressure of the atmosphere. There's a lot of square inches on this jar. Times 14.7. It's a lot. Okay? But now as soon as I let the air in, now it's pushing out with the same force the atmosphere is pushing in. Then I just have to overcome gravity. Okay? Why did that stick? Okay? Is that? Stick your finger in there. It's not hot, right? Okay? But yet it was boiling.
Chemistry takes everything you know and just says, no.
All right, so if you've ever been in the mountains, gone skiing, there's high altitude baking instructions. Because what happens to atmospheric pressure as you go up? It gets less. So what does that mean about the temperature of the water boils? It'll boil at a lower temperature. So again, once water begins to boil, it stays at a constant temperature. So your spaghetti noodles are going to be trying to cook at 90 degrees rather than 100 degrees Celsius. So it's going to take longer to cook your food because the water's boiling at a lower temperature, and that's the maximum temperature it can get to because all the energy is being used to break the bonds. Okay? So, boiling. If you have weak attractive forces, what type of boiling? You're going to have a high or low boiling point? Low. If you have strong attractive forces, high. Okay? But it's all related to the vapor pressure of the liquid. So we can make a substance boil based upon the temperature and the pressure exerted on it. So, now we need to look at how do we measure pressure. Go back up to 11 and 12. I'll be right back.
Just watch water boil when it must be hot. This class is so trippy. It's like, dude, Godzilla vs. Kong. That's such a dumb movie. Like,
How can we get there?
I feel like all this is fake.
with an absolute lava spit
I
dragon
feel
teeth.
like I understand it now.
Let's do a big
and
monkey.
like, and you know, I'm like, okay, I get that.
Big monkey hit
But
hard.
then it's like, what?
Dragon.
Yeah, there's like.
Like,
it's
oh,
like
that
those
makes
are
sense
like
how it,
long
how it
ago.
bounces off and evaporates.
Like back in the 80s, like they made like Converse Godzilla.
We have about an hour. An hour.
Yeah, I don't know say it was stupid that they do it because they made it so long.
Maybe of HBO you can watch it. Imagine there's 32 of those sides.
Okay.
It's a big tube.
It is a big tube. This is called a gas collecting tube, but it's just really looks just like a big test tube. Okay? But this costs like $25. So you don't want to break it. And fill it up with water to the tippy top.
I think we're gonna break that.
Okay, so now I'm going to take my thumb. So can you see that it's kind of right to the very, I don't know if you can see or not, but it's to the top. We got a little bit of a curve on the top, okay, because water's cohesive forces. We want to make it in the lowest surface area. So a sphere is the smallest surface area that a substance can get. That's why water forms droplets. Okay, so I put my thumb over it, stick it down in the liquid, and wait a second. None of the water came out. Why is this water defying gravity? Why doesn't, this is the same thing as when you're playing with your soda at McDonald's with the straw, and you put your finger over it and take it out, and it doesn't come out? Why not?
Because there's still pressure in the tube.
There's pressure. I don't know, it just always works. I just put my finger over it and then I can drink it out of the straw. I don't need to know why or how it does that. I just know it does.
Does it lower the pressure?
This is the same reason the vacuum works.
'Cause this thing's sucking?
I don't know, I'm asking questions.
Okay? If this liquid water comes out, what's gonna happen to this liquid level here? It's gonna go up. What's keeping this from going up? The atmospheric pressure pushing down on the surface of this liquid. We don't think about it, but the atmosphere is pushing down 14.7 pounds on every square inch. Well, this doesn't weigh 14.7 pounds. So in the push of war, gravity pulling this down, atmosphere pushing down, the atmosphere is winning. And so the water stays up here.
So if you were to not fill that all the way up, where would the water just like?
Well, I mean, if I didn't fill it all the way up, then it would just however much I put in here, then it technically would be a vacuum up above here. Because the air can't, once I put it under the water, the air can't get in. Now, let me change that. If I only filled it up to here, then I turned upside down, the air that's trapped in there is gonna be up here. And so now there's some more pressure pushing down, so the water doesn't, the atmosphere can't push the water back all the way up here because this air is pushing down enough to keep it like to there.
So is that why when we take the straw, sometimes we can make the stuff float in the middle?
Yeah, exactly. All right, so if I want to get a column of water that's going to have the same downward 14.7 pounds per square inch, anyone know how tall? Anybody scuba dive? Nobody scuba dives? It's on a bucket list. I'm going to learn how to do it this summer, and then I'm going to go to like St. Thomas or somewhere, and we're going to scuba dive. My wife wants to do it too. So then we'll go skydiving and possibly do the skydive into a submarine, into a scuba dive.
Skydiving's not worth it.
Oh, I've already been once.
Well, yeah, you can only go once.
No.
It's like, you got one
I
shot.
survived.
I would never do skydiving ever.
Oh man, I want to go to where unfortunately I had to do tandem, and so Steve and I got really close. The guy that was my guy was Steve too. So
Your parachute. I'm good. No thanks.
all right, so the reason I say scuba diving because if you every 33 feet you go down.
You get to stop or whatever, don't you? Like,
Well, you do as far as because, and we'll talk about that in the next unit with gases. But every 33 feet you go down, the pressure doubles. You got 2 atmospheres of pressure at 33 feet. At 66 feet, you're at 3 atmospheres of pressure. Okay, so you're adding, every 33 feet is an atmosphere. So if I wanted to make a test tube, I could make it 33 feet, really make it about 34 feet tall. Fill it up to the tippy top. That'd be like outside this window right here, because each floor is about 10 feet. Okay, so if I go to out this window to the ground, and I had 34 feet up here, filled it up with water, put my thumb over it, put it down in the beaker down at the bottom. Okay, then the water is going to come down until it equals the weight of the atmosphere. Then if a high pressure system comes through, it pushes down harder on this, what's going to happen to my water level? It's going to rise. If a low pressure storm comes through, lets up some, this is going to drop down. We've created a barometer. A barometer measures atmospheric pressure. Okay? That's somewhere in number 11 says something like that, doesn't it? Atmospheric pressure is measured with a barometer. B-A-R-O-M-E-T-E-R. Now, 33-foot barometer is not very practical. So what liquid do they use instead? Mercury, because it's 13.55 times more dense than water, which means we only need to have a column 760 millimeters tall, which is this tall. So we'd only have to have mercury this tall, and then so somebody at the mercury factory takes a tube like this, that's at least, it's probably going to be about this tall. They fill it up with mercury, put your thumb over it, and put it down into a bowl of mercury. Then the mercury is going to come down until the weight of the mercury going down is equal to the atmospheric pressure. We say standard normal atmospheric pressure is 760 millimeters of mercury, and I'm going to put all these on the board for you in a second. 760 millimeters of mercury. That's the height of a column that air will support. Okay? So 1 atmosphere is equal to 760 millimeters of mercury. Now, the guy that invented the barometer's name is Torricelli. So they gave millimeters of mercury a unit named after him, which is 760 torr. So a torr and a millimeter of mercury are exactly the same thing. Now in America, we refuse to switch to the metric system. So when you watch James Spann and he's talking about the barometric pressure of a different storm and hurricanes, a lot of times they talk about the pressure. That's going to be 29.92 inches of mercury. That's the same height, just in inches. So in America, we do barometric pressure in inches. Everywhere else, you do torr, millimeters of mercury. Now, this is, we already said, this is 14.7 pounds per square inch. Okay? Now, has anybody, you put air in your tire, maybe it's a bike tire or car tire, you have a little gauge where you push it and the little thing pops out the end? Everybody know what I'm talking about? You've never measured tire pressure with a little gauge where
Oh, yeah, yeah.
you put it on there and it pops out. There's a black scale and a red scale on it. In America, we always read the red, black scale. Pounds per square inch, PSI. Normal car tire pressure is anywhere between 32 and 35 PSI. Okay, you'll have your little car, low pressure light will come on, you have to go check it. You'll be down at 28, 29 PSI. You got to put some air in it to increase the pressure. But if you ever look on the other side, it says KPAs. That's the actual metric unit, the SI, that's what the rest of the world uses. And this is equal to 101.3 KPAs. Kilopascals. It's a measure of pressure. Now, this is the actual metric. This is the SI unit, System International Unit. That's the metric unit. Okay? But this and this, which is the same as that, are the ones that we're going to use almost all the time. These are most commonly used, but that's the actual metric unit. And that's what's on the other side. If you ever go and look at, if you have something in your car, glove box, or in the console, you probably have at least I do, I have a tire pressure gauge. And you look at it. Got KPAs on the other side. All right? Because that way they can sell it around the world, not just in the US. So this is how they measure pressure in terms of millimeters of mercury. We use a barometer. How much is the atmosphere pushing down? We can measure that. But what about measuring the vapor pressure of just a normal, like alcohol? Then we have to use a thing called a manometer, manometer. And the way a manometer works, let's just say I put some alcohol in here. And I have it hooked up to a tube. And I fill this tube with mercury. Okay? So the levels are equal. I have a valve right here that closes this off. The alcohol is going to begin to evaporate because the alcohol evaporates. When I open the valve and let this go, it's going to push down on that surface. So what's going to happen to this set? It's going to go up. So now we'll end up with this being down here and this being up to here. So now I'll measure from here to here, and that's my millimeters of mercury. That's the pressure exerted by the vapor above this liquid. Now if I increase the temperature, it's going to evaporate more. We're going to have more gas molecules coming across, and so it's going to push down with more force, and so it's going to push it up higher. We'll get a greater vapor pressure. So a manometer measures the vapor pressure, a barometer measures atmospheric pressure. That fill in all the blanks?
Wait, will you say that again, just so, like.
A manometer measures vapor pressure. while a barometer measures atmospheric pressure. But both measure in terms of millimeters of mercury. Now we've talked about the rest of these, but let's just go ahead and fill them in. Okay? So we know boiling occurs when the vapor pressure of a liquid equals atmospheric pressure. If a high pressure weather system is in place, the boiling point of a liquid is what's gonna happen to the boiling point? If you put more pressure on the surface, it's gonna take more energy to make it boil, right? That's how a pressure cooker works. Have any of y'all ever heard of a pressure cooker? It's actually what the Boston Marathon bomber used to fill with all of his nails and made his bomb out of that. He used a pressure cooker. They use them a lot in the mountains because the pressure is low. A pressure cooker, rather than having an open container where the steam can come off, you have a sealed container. The lid seals down tight. So as the water begins to get hot and the vapor collects above it, the pressure above the water, the vapor pressure increases. So the higher the vapor pressure, then the water can't boil at as low a temperature. So you can get the water to boil at 140, 150, 160 degrees Celsius. And so food will cook way faster then because of the high pressure. So if you increase the pressure, you increase the boiling point. Now there is a max to that. There is a max. Come on. Fine. We look at this graph right here. This is what we call a phase diagram. We can control the state of any substance by controlling the pressure and the temperature. Anywhere along this line, as you go and mix, so at this temperature and this pressure, ice is right at its melting point. Anything temperature below this is going to be a solid. Anything above, it's going to be a liquid. This whole line, this is that vapor pressure curve that we were just looking at on the other graph. So the vapor right here is curving up, going to here. So at 1 atmosphere, we say this is the normal boiling point. But if I increase the pressure, now the boiling point is not going to be till out here. If I decrease the pressure, then the boiling point will be down here. To get it to boil at like 20 like I did right here, I had to have the pressure almost a complete vacuum. So we can control the state of the substance. Any of y'all been ice skating at Pelham? Okay? The ice, and steel actually has a pretty high coefficient of friction. There's a lot of friction between the blade. But when you put the pressure on the ice, it actually melts the water below your skate. Because you're increasing the pressure, which is decreasing the freezing point. It's called regelation. You don't need to know that, but it's R-E-G-E-L-A-T-I-O-N. Kind of a cool demo would be if you had a block of ice, you could take a piano wire and you have it in a freezer. You have a block of ice in a freezer. Put a piano wire with a weight attached to each end, putting pressure on that wire. That wire pressure will melt the ice and drop down below it. But then the pressure is off of the water that's above it now, and it'll refreeze. So that piano wire will work its way all the way through that block of ice, but the block of ice will stay together. Because it's constantly, it's melting it as it's putting pressure on it, it's taking the pressure off, it's refreezing above it.
So you just at some point have a wire that never was
Well, it just, the wire just, again, the block of ice, you have the block of ice, and then the wire is draped over it like this with the weights on the end. So it goes to here, it gets liquid above it, because it melted it. But when it takes the pressure off, when it's below it, now there's no pressure on it anymore, so now it refreezes back at the normal temperature. So it's constantly melting, freezing, so the wire ends up going all the way through, but the block of ice stays intact. It's called regelation. So we can, again, we can control the pressure. Now notice right here, what's that called? The triple point. There is one temperature and pressure, 0.0060 atmospheres and 0.01 degrees Celsius. Water can actually be ice, water, and steam all at the same time. Now, to try and show you how that can be,
Is that like what, dry ice is?
well, dry ice actually just goes straight from solid to a gas. But if you put enough pressure on it, just a little bit more pressure, you can make it do a triple point as well. This is probably gonna mess up. All right, so I'm gonna take just this is a sidearm flask, some cyclohexane. Obviously it's a liquid, it's a hydrocarbon. Okay, so I just have some in there. Put this into the vacuum. Making sure I get a good seal. I'm going to turn the vacuum on. Now as I'm decreasing the pressure in here, the boiling point will be decreasing. Okay, so now it's boiling. And it should go to a solid. It's supposed to go to a solid. There it goes. Okay, because now you can see some of the solid forming on the side. So it's a solid, it's a liquid, and it's boiling as a gas all at the same time. Now eventually it all freezes. Because what do we know about the evaporation? It's cooling it off. And so now it's gotten cold. But now you put the pressure on it. Okay? So, I mean, now you feel it. It's like ice now, okay? Because all those high-speed molecules left and it cooled it off. But for a moment, you had a solid, you had a liquid, and the liquid was boiling, so you had a gas. We were at the triple point. Now, it's only one very distinct point. Notice that once the pressure gets so low near a vacuum, it's always a vapor. Okay, because there's nothing kind of holding the molecules together at all. Notice we come up here, there's a max. Once you get above 373.99, you have to have 217.75 atmospheres of pressure on the water to keep it from boiling. But you can get water, liquid water, up to 373.99, so 374 degrees Kelvin. It is Kelvin. No, Celsius. Pardon me, Celsius. Which is 273 above its normal. But you have to have this tremendous amount of pressure. Now you go to 375. It doesn't matter if you put 1,000,000 atmospheres of pressure. It's going to be a vapor. The critical temperature is the highest temperature a substance can remain a liquid under any amount of pressure. The critical pressure is that minimum amount. We have to have at least 217.75 here to make it stay a liquid at its critical temperature. Now, critical temperature is another measure of attractive forces. The stronger the attractive force, the higher the critical temperature. Okay? Now, water is very unique because increasing the pressure actually decreases the freezing temperature. Okay? Now, I bet all of you have experienced this. Have you ever had a soda in the back of the fridge and you take it out and you open it up and it turns into a slushie? Never seen that. My Mountain Dew this morning actually did it from my fridge in here. Okay? I remember the first time I experienced this, I was just out of college. I was living on my own in a roach-infested house with 3 other guys. Okay, right near LSU. Okay, we weren't in the ghetto, but we could see it from our backyard. So, I came home from church and I bought Coke in a bottle because Coke in a bottle was the best. Okay, didn't have that plasticky taste. I put it in the freezer though because I wanted it cold. Well, I went up, started watching football. I forgot about it. And then I remembered, oh crap, ran down, pulled it out, it was all liquidy. Oh, yes, this is gonna be awesome. It's going to be super cold. It's gonna be it's gonna be great. My mouth was watering. And I go and I open it up, and all of a sudden it just turns all into a Coke icy slush. It comes flying out of the top because, ice expands when it freezes. And so it came flying out, made a big mess. And then, I was very disappointed. But after I got it cleaned up, I started, now why did that happen? What's going on here? Well, we already talked about water having this open crystal structure, right? So in order for water to freeze, it has to expand. But when you put pressure on it, you keep it from expanding. So it can't open up. So the pressure is keeping it from being able to form those hydrogen bonds and expand. The minute you take that pressure off, pop the top, now the water has the freedom to form those hydrogen bonds, and they form almost instantly. Okay? So the water, and you guys will experience this at some point in your life. Put a Coke in the back of the refrigerator, or put it in the freezer.
Does it work in like plastic bottles?
Mm-hmm. Yeah, seriously, my Mountain Dew this morning that I got out of that fridge, it wasn't this one, but actually had a little ice on the top of it when I opened it up. Okay, I'm at my wife's house in Northport, which we're trying to sell. I had Gatorade, a Powerade in the back, and it was frozen. But it wasn't under pressure, so it was just frozen. But the refrigerator will freeze them sometimes if you put it in the back. Just try it.
My refrigerator don't work like that.
Put a Coke in the freezer for an hour. Then take it out and open it. Okay? You'll see it just kind of turn into ice automatically. Maybe 30 minutes. Don't let it explode. Because if you put it in there too long, it will actually finally all freeze. Because, it's only lowering the freezing point a little bit. Now, every other substance, not every other, there's like 3 substances that expand when they freeze. Most substances, you put pressure on them, you're forcing them together, you help it to become a solid more. So this line tends to have a positive slope to it. Okay, so this line for most substances goes this way. Water's just rare for it to go that way. Okay, phase diagram: solid, liquid, gas. We can control the phase by controlling the temperature and pressure. Boiling occurs when? So how do we normally make the vapor pressure equal atmospheric pressure? We heat it up. But if we go up into the mountains, the atmospheric pressure is less. So what does that mean about the boiling point? It's lower. Okay, those are the things you need to be able to kind of keep straight. Okay? All right. So now, let's have some math fun. We did not do at the beginning of the year, we didn't do any Q problems where Q equals MC delta T.
No,
You never heard that Q equals MC delta T?
no.
Okay, Q equals MCAT. See, a lot of times I cover that in second chapter when I'm talking about heat versus temperature, when I'm introducing the concept of potential energy and kinetic energy. But because of time, and Mr. Graber likes to do it now, I conceded, but I can't ever remember something from year to year when I do it. Okay, this unit is full of graphs. Oh, and this is hopefully elementary, but we should know the names of all the different phase changes, right? You know that solid to a liquid is called melting. Liquid to a gas solid is called freezing. You have evaporation or boiling, and then condensation is the reverse. That's, when you have your glass of iced tea and the water collects on the outside of it, okay? Condensation. Dew on the ground is condensation. And then dry ice, it's sublimation going straight from the solid to the gas. And then snow is water vapor actually freezing and becoming going straight to a solid, and we call that deposition. Okay, so we should just know the basic names of phase changes. All right, where is the cooling curve? I should know these page numbers, but I never read the book. Put glasses on. You guys need another break anyway. Where is the stupid index?
Are you the Russian?
Yeah.
So I feel like this is the part on being very full of things.
Yeah, all this depth around right here. You just fast forward. Shoot. All right. I thought for sure it was in that chapter, but I guess I should have actually looked. I know exactly what I want. Curves 459 and 460.
Which one is the next one we get again?
We go to 35, dude. Alright,
Thursday's one, so.
this is called a heating curve, and you might want to draw it just in your notes somewhere, okay? So we've talked about phase changes, boiling points, melting points. So what temperature does ice melt?
33.
33.20, anything above 32.
Yeah.
Anything above 32, okay? What temperature does water freeze?
Anything under 32 and under.
Okay, so 32 is the freezing, but you're saying melting has to be above 32. What happened on the boiling? Did the temperature change while it was boiling? So the boiling was 100 degrees Celsius. So at what temperature will a gas turn back into a liquid? Does it have to be just under 100?
Has to be out of them.
Okay, it has to be at 100. Remember, phase changes involve breaking and forming bonds. What type of energy is that? Kinetic or potential? Potential. Breaking and forming bonds is potential energy. Okay? Potential energy, PE, is called latent heat because it is hidden to a thermometer. It is hidden. That's what latent means, to the thermometer. So in other words, if you're changing potential energy, the temperature doesn't change. Thermometer does not measure. A thermometer measures what? The speed, the average kinetic energy. So if you're making the molecules move faster, you're going to change the temperature. But if you're going to actually cause them to break bonds or form bonds, you're going to be changing their potential energy, which doesn't get measured by the thermometer. Thermometer only measures changes in kinetic energy. So if I'm looking at this graph right here, I'm starting with water at negative 25, which means it's ice. I have to heat the ice up. It requires a change in kinetic energy in order to get from negative 25 to 0. Now, as soon as I get to 0 degrees Celsius, 32 Fahrenheit, it begins to melt. But notice what's happening to the temperature. Stays the same, because when I'm melting, I'm breaking and stretching the bonds. I am not making the molecules move faster. Now the energy is going in to stretch and to bend the bonds of the water. So it goes from here to here as it's melting at constant temperature. So I'm going to ask the question again. At what temperature does ice melt? 0. At what temperature does water freeze? 0. The melting point and the freezing point are the exact same temperature. But they don't have the same amount of energy. Water has more energy in it than ice does. But it's potential energy that's hidden to the thermometer. It's latent heat. It's energy that went in to move the molecules apart, that when they can come back together, they have the potential to release that same amount of energy. That energy released, okay, let's just say the energy required to melt 1 gram of a substance at its melting point is called the heat of fusion. And we represent that with WH sub F. The heat of fusion. So once I get ice to 0, I have to add in this heat of fusion in order to make it become water at 0. Delta HF for water is equal to 334 joules per gram. So what does that mean? I have a gram of water. It's at ice. I heat it up. I get it to its freezing point, 0 degrees. I have to add in an additional 334 joules of energy to make it become water at 0 degrees. This is all latent heat. This is all potential energy hidden to the thermometer. Okay? So now, what's going to happen when water freezes? What's it going to do with that energy? It's going to lose it. It's going to release it to the surrounding. That's the whole peach thing. When that water freezes, temperature is going to stay the same, but it's going to release that 334 joules per gram to the surroundings, to the peach. That's a difference in potential energy. Same temperature, but water has more total energy than ice does at the same temperature. Now, once it's all melted, then we begin increasing the kinetic energy again. The temperature begins to change. We get a slope on our line until we get to the boiling point. Now we have to break the molecules completely apart from one another. Again, potential energy. We're going to call this the heat of vaporization. So anybody have a calculator out? I can never remember this number. I know it in calories. 539 times 4.184.
2,255.17.
That's what I wanted to remember. Delta H sub F is equal to 2255 joules per gram. Notice it's much, much larger than here. Delta H of fusion is equal to 334 joules per gram. Takes a tremendous amount of energy to cause water to go into steam, because the water has a very strong hydrogen bonds. It takes a lot of energy. So steam, so if you're having a very bad day, somebody pours boiling water onto this arm, somebody blows steam at 100 degrees on this arm. Okay? This arm is going to be burned much more severely, because as the steam condenses and goes from here to here, it's going to release this much energy per gram into your skin, as well as the kinetic energy that the water would have over here. It has all this extra potential energy inside of it. The ability for those bonds to come back together and to release that energy. Steam will burn you very, very badly. Okay? So, if we have a temperature change, to measure energy, if the temperature changes, and this is going to be Q, if the temperature changes, Q is gonna equal MC delta T. Maybe get another sheet of paper out. Doesn't all have to be on the same sheet.
Yes, it does.
There's gonna be, I'm about to give you a new sheet that you can use the back of. But Q equals MC delta T. Now in MC delta T, M is equal to the mass, C is equal to a thing called specific heat, which I'll define in a second. And delta T, what does the delta mean? Change in. The change in temperature. Okay? And since it's change, it can be Celsius or Kelvin because it's going to be the same number. All right, what is this specific heat thing? Energy required to raise 1 gram of a substance 1 degree Celsius. Yeah, why didn't you turn yours in?
I didn't,
I know, why not?
I don't know.
You need to turn them in.
Yeah. I just saw the piece of paper and thought about it. No,
I thought you just looked at I now and so you're 0.
No, I haven't checked it out like a week.
Okay, so the specific heat of water is C, is 4.18 joules per gram degree Celsius, whereas aluminum is 0.9. So what does that mean? If I have a gram of water, I'm going to have to put in 4.18 joules to raise that gram of water from 1 degree to 2 degrees. Or from 2 degrees to 3 degrees. For every gram of water to be raised 1 degree, I have to put in 4 joules of energy. But how much do I have to put into aluminum? 0.9, right? So it's a lot easier to heat up the aluminum. Have you ever taken aluminum, a baked potato that's wrapped in aluminum foil out of the oven? If you can just get one corner of the aluminum foil up, you can roll the baked potato out of it. But the baked potato is full of water, so I mean it's still piping hot even 5-10 minutes after you take it out of the oven. But the aluminum foil cools off almost immediately. Specific heat, to me, the way I think about it is how much does 1 degree change in temperature cost in terms of joules? And I think of it like this. We each have $100. I give 2 people $100. One goes to Saks Fifth Avenue to buy clothes. The other one goes to Old Navy. Who's going to come out with more clothes?
I don't know what sex is. I thought it was like something like,
No, Saks Fifth Avenue is high end.
okay, Old Navy then.
Saks Fifth Avenue is high end stuff. Okay, $100 might buy you 1 shirt. Old Navy, you generally get 3 for $10. You know, high quality. All right, but you know they serve their purpose. I have a lot of clothes from Old Navy. I don't have anything from Saks. And so that's the same thing. How much energy does it take? The lower the specific heat, that means that the temperature, the change in temperature costs less. So you can get more for your money. So if we put 100 joules of energy into a gram of water and 100 joules of energy into a gram of aluminum, the aluminum is going to go up way more degrees than the water is. Because the degree costs a lot less. So the specific heat is that measure of how much heat do I add versus how much is the temperature going to change. So if I want to measure, anytime there's a temperature change, I can measure how much energy it's going to take with this equation. Now, if y'all want to go to med school, you're going to have to take the medical college admissions test, abbreviated the MCAT. Okay? This equation is Q is equal to MCAT, because the delta looks like an M. Q equals MCAT. That's how we measure the energy needed. So if I want to measure how much energy does it take to go from 25 degrees to 75 degrees, and let's just say it was 50 grams of water. Well, Q is going to equal 50 grams times specific heat. It's always 4.18 joules per gram degree Celsius. Then my change in temperature from 25 to 75, what's the change? 50. And it's always final minus initial, and I'm just going to put it there just to kind of show that. But that's how much joules it's going to take to raise that water from that temperature to that temperature. Anytime there's a temperature change, we use MCAT. But if there's a phase change, whew, gotta fight through. We're so far behind, we can't slow down. Ready? Okay, so I'm continuing on this right here. If the temperature changes, we do all of this. If the phase changes, energy is used to break or form bonds. Okay? Always requires energy to break bonds, always releases energy when bonds are formed. Just think of breaking up is always hard to do. Okay? You need to break up with your boyfriend, your girlfriend, whoever. Okay? You're stressed about it. You know, nowadays you can just text them, you know, and just say, hey, let's just be friends. Okay? In my day, we had to actually call them on the phone, talk to them. Okay? It's a big deal. Okay? It's hard to break up. I mean, it's, you know, they write songs about, you know, breaking up and crying and all that stuff. It's never an easy experience. Breaking up is always hard to do, always requires energy. But when bonds begin to form and sparks begin to fly, that's when energy is always released. Okay? And so that's when things really begin to heat up, is when those bonds begin to form. Forming bonds always release energy. Breaking bonds always requires energy. Okay? But in this case, in phase change, it's going to be the same energy just going in and out. So, this is potential energy which occurs at constant temperature. All right, so for melting, Q is going to equal the mass times your heat of fusion. If it's freezing, it's going to be the same equation, it's just going to be released instead of, so it'll be a negative value versus a positive. Freezing, Q is going to equal negative mass times heat of fusion. So for boiling, Q is going to equal what? Look up there. When we boil, what heat do we have to put in? And I put an F. Supposed to be a V, sorry. Mass times your heat of vaporization. And then for condensing, Q is going to equal the negative mass times your heat of vaporization. Now the good news is you'll always be given that number. Okay? All right. Finally. Supposed to be through all of this by the end of today. Of course. This is yours to keep. We're gonna work through this. Okay, so notice all these values that are given at the top. And an interesting point is that the specific heat of ice, steam, and water are all three different from each other. Ice and steam are close, but water is just way higher than both of them. Okay, so you have your specific heat of ice, your specific heat of water, the specific heat of steam. You have the heat of fusion of water, and you have this used a little bit different value, but it's close enough. I said 2255, we'll use 2264. Okay? So, given water, now, this is joules per gram. This is kilojoules per mole. What does this mean? This is a conversion factor between joules and grams. So I just kind of heard mumble. Okay, what's this a conversion factor between? Kilojoules and moles. Okay, so these are all just conversion factors. This is all conversion. Given that water has a molar enthalpy of vaporization, that's this. Okay, what's it say? How much could be vaporized? How much water could be vaporized by 443 kilojoules? So I'm going to start with my given, 443 kilojoules. That's over an understood one. So start with what's given, find the appropriate conversion factor or factors, and set your units up so they cancel. I want to given how much water, so I'm looking for kilojoules, I'm looking for grams of water. Well, but I have kilojoules, so what conversion factor do I have with kilojoules in it?
40.79.
And where does that need to go?
The bottom.
So I'm going to say 1 mole over 40.79 kilojoules. Now if I stopped right there, what is that going to tell me?
The mole of water.
Moles of water, right? But what's the question asked for?
Grams.
How do we go from moles to grams?
Molar mass.
Molar mass, and we've memorized the molar mass of water to be 18.02 grams over 1 mole. So now I have grams, which is what the question's looking for, so we just calculate it out. So our enthalpies, these are conversion factors between joules and grams, kilojoules and moles. $195.7, and how many sig figs should we have?
2 out from the decimal.
4. No.
3.
3 total.
196.
196. Was it 195 point something?
It was 195.7.
Yeah, 196. And that's going to be grams of water. So 443 kilojoules would be able to convert 196 grams of water to steam. But the water already had to be at 100. This is just once it's 100, you could put another 443 and 196 grams of water would evaporate off. All right. Let's look at the next one. How much energy in kilojoules would be needed for 33 grams of water to go to steam compared to 33 grams of ice going to water? So we got to do 2 here. What do we have to do? Well, we have 33 grams. We'll just say, this is going to be liquid to gas. And then B is going to be solid to liquid. So we're going to have 33 grams, right? What conversion factor do we have that has grams in it?
Molar mass.
Molar mass. Okay,
And
and what else? But because we want, does anything that relates energy to grams,
the change H and B.
which is how, what number?
334.
Now this is liquid to gas.
2264.
The 2264, right? It's 2264 joules per gram. So where does joules need to go?
The top.
2264 joules for every 1 gram. Now how do I go to kilojoules? So 1 kilojoule over 1,000 joules. And this only has 2 sig figs, so
It'd just be 75.
75,
Because it's 74.7.
okay? So what would we do on B, solid to liquid? What's the only thing that'd be different?
Change it to 264 and 334.
To 334, that's exactly right.
Right here, would we write C or would we just do H2O?
You can still just do H2O because ice, water, and steam are all H2O. So again, I'm going to say 334 joules per every 1 gram times 1 kilojoule over 1,000 joules. So we'll say 11 kilojoules. So it only takes 11 kilojoules to melt the ice, but it takes 75 kilojoules to boil it. Because melting just causes you to stretch the bonds. Boiling causes you to completely break them apart. Requires much more energy. Wow. Okay? It is found that 34 joules of energy are required to melt 7.3 grams of a substance. The molar mass of the substance is 59.8 grams per mole. Calculate the enthalpy of fusion in kilojoules per mole. Okay? Delta H of fusion in kilojoules per mole. That's what the question's asking for, right? So what 2 things do we need to find? If I want the delta H of fusion in kilojoules per mole, what 2 things do I need to find? Kilojoules and moles, right? Well, how much energy, do I know anything about kilojoules? What's the problem, tell me? 34 joules. Now can you do the conversion in your head without writing it out? How many kilojoules is that? 0.034. You move it 3 places left. Okay, you're dividing by 1,000. However many zeros there are in the number you're dividing it by, that's how many places you move it. So it's going to equal 0.034 kilojoules. But I need moles. How do I find moles?
7.3 grams.
Times?
Not divided.
What divided by what? We want to go 7.3. Always start with the given. Grams. Times. What? How do we go grams to moles?
1 mole over 18.02.
No, this isn't water. It's the substance. What's the molar mass of the substance? 59.8. If it were water, you would do that. That equals
0.122.
And now technically we should only have 2, but I like to carry 1 extra and we'll round off at the end. So we know we should only have 2 sig figs because of that. So that's my moles, so that's what I put here. So we end up getting
0.279.
0.279 kilojoules per mole. All right. We're going to wrap it up with this. Tomorrow, we're just going to keep working these problems. Okay, so we know this is going to be ice, this is going to be water, liquid, and this is going to be steam. What's happening going left to right? Here. Heat added, but what phase change? Liquid to gas, which we call boiling. That's what I'm looking for. And then coming this way, it's condensing. This is melting. This is freezing. Anytime you're here, Q is going to equal MC delta T. Here, Q is equal to mass times heat of fusion. Q equals MC delta T. Q equals mass times heat of vaporization. Q equals MC delta T. So if I want to figure out, and we'll do this tomorrow, this is what the last 2 problems are like on that sheet. Okay? And that sheet didn't have a back, did it? It's supposed to have a back. I may have to get you the second page tomorrow. We'll see. All right, but if I want to go here, if I wanted to find out how much energy does it take to go from here to here, I'm going to have 5 Q's. I'm going to have to do them independent. You can't just do one big equation. You're going to have to figure out how much energy does it take to go from here to here, then how much does it go from here to here, then how much does it go from here to here, then to boil, and then to the steam. So you do Q equals MCAT plus M equal times heat of fusion plus MCAT plus heat of vaporization plus MCAT. You just add them all together. And tomorrow we're going to practice, anywhere starting, any starting point, any ending point, where do we go? And that's going to end our states of matter discussion.